Like maybe it's true that like theory is somehow more philosophically interesting than just like benchmark applications, like than just empirical pursuit on methods. But the application is like a different axis. I actually think that like the applications are super philosophically interesting. Like I think they force you to ask, because they ask you to ask questions that aren't just like mechanical. You have to ask like the normative questions, right? Like the thing that I think is exciting about applications is that nobody told you in the first place what is worth predicting. Like that by itself, like convincing someone that like this is actually a problem worth solving.
You're listening to Gradient Descent, a show where we learn about making machine learning models work in the real world. I'm your host, Lucas Bewald. Zach Lipton is a professor of machine learning at Carnegie Mellon University. He has an incredible number of research interests, and it's actually hard to research all the papers that he's been working on prepping for this interview. I'll give you a couple topics that we might cover today: robustness under distribution shift, breast cancer screening with machine learning, the effective and equitable allocation of organs, and the intersection of causal thinking with messy data. He's the founder of the Approximately Correct blog and the creator of Dive into Deep Learning, an interactive open source book drafted entirely in Jupyter notebooks. Couldn't be more excited to get into it. You know, I have a couple of your papers that you flagged that I'd love to talk about, but kind of before then, I kind of wanted you to catch me up. Like, I feel like last time I knew you were applying to grad school, and now you seem like a successful professor with a lab at a very famous school. What happened, Zach?
Yeah, it's been a weird ride. So when we met, it was in San Francisco, and that was like I had already made this like weird decision to like go and kind of do this tech thing and kind of live in California for a year, get into grad school. But before that, I was a musician, so it was even a bigger jump. I think it like looks more planned or directed now than it was at the time. The guiding thing to get from being a musician to being like a PhD in machine learning was just like a recognition that I wanted to be in PhD. It was like I had enough friends who were in the sciences that it was just like I sort of like knew that maybe like the sorting hat got it wrong or something at some point. And like I didn't even know what modern machine learning was. It was really guided by like a kind of, I knew I wanted to be in a certain kind of scholarship and I wanted to be in a certain kind of environment. And like I knew that meant going to grad school. And then sort of looking like, all right, I was an old man for like a first person starting on a scientific career. So I was like, I wasn't going to do like a wet lab thing and like spend 10 years learning how to like pipette because it was too late for that. And I had like just enough of a connection with computer science earlier that like I knew that was something I enjoyed doing. But I don't know, it's kind of weird to look back. I mean, I think in terms of like from where we met, which was like I was like kind of knew almost nothing. I was just kind of wanted to go to grad school for machine learning. I think the biggest thing is that I entered the field at the moment of like a really great leveling event. So the like sudden rise of deep learning was like an unexpected thing. And I think it would be an exaggeration to say it like completely wiped out people's skill sets or whatever from before then. But it certainly like opened up like a path in research where at least like the next 2-3 years of steps in that direction, or a good chunk of them, didn't really require that you were like, you know, like if things were just progressing normal science and it was like kernel machines were dominating, like for me to get to the point where I was like a world leader in, you know, understanding non-parametrics or something, wouldn't happen in like 3 or 4 years. But like entering a field where suddenly like everyone was doing deep learning and there was like kind of like a, you know, like a Wild West type environment, made it very easy to sort of like pick an area like say ML and healthcare and very quickly be at least like on now like the new generation of technologies, be one of the leaders like applying deep learning in that. So I think I got lucky that I sort of entered at that moment of transition where it wasn't so disadvantageous that like I wasn't an expert in like, you know, I wasn't a great engineer and I didn't necessarily have all of that mathematical background, but I was able to sort of like one advantage of it is I didn't have a lot of commitments. So I wasn't like committed to a set of methods that like I had invested years and like reputation in getting them to work. So I could be kind of nonpartisan about it and say like, this is clearly a thing that's happening and I have like no sunk costs. So, you know, get in there.
That's really cool. It's actually kind of inspiring. I like it. What was your like initial research on like when you got to grad school? What were you looking at?
I was working on healthcare problems. So I had some like personal health experiences that were pretty like devastating earlier in life. And I think that was just sort of always like a motivating thing of, could we be making a lot of these kinds of inferences better that guide medical decision making. It still is a kind of like overriding, like organizing, like motivation in my work. My research is a little more diverse. Like I don't just do like I want to grab things and get empirical results on, say, like a specific medical data set. Although I do have a bunch of research in my portfolio that's like is applied medical work, but also like the motivated kind of underlying like theoretical and methodological problems. But like that was how I started PhD, was working on medical stuff. It was like I wrote a statement of purpose that I think was like caught the attention of some people. Like at UCSD, which is where I ended up doing my PhD, there's a division that does biomedical informatics, and there's a computer science department. One's in the med school, the other's in engineering school. And I think like they had been talking about maybe getting a joint student at some point, or someone who would be funded on one of the medical informatics training grants but be a student in CS, and they were looking for someone like that. What I was hired to do essentially was to work on healthcare problems. But I kind of like just sort of, I started with that motivation and looking at what people are doing. But I was sitting in the computer science department and watching what's happening with machine learning. So for example, I suppose like the first problem I worked on was something in text mining. So it was medical articles, and we were doing like massive multi-label classification. So all the medical articles that get indexed by the NIH are tagged with some subset of this like large controlled vocabulary, like kind of enables things like systematic reviews of the literature. Mm-hmm. And so just like a simple, like back then we were using linear models, and the challenge was that it was 27,000 classes and we're trying to predict them all and do it in like an efficient way. Now it seems kind of quaint because it's like, you train language models with like billions of parameters and vocabularies that are like 300,000 words, and it's not that big a deal. So I started working on that, but I was seeing what was happening in deep learning. And I think like the first kind of bigger break that wasn't like just a kind of minor paper was we were sort of watching everything that was happening. It's like convolutional neural networks were maybe the thing that were catching the most attention, 2013, 14. Mm-hmm. But I was interested in a lot of these problems that had more sequential structure. So I was looking at medical time series data, like people are admitted, there's a bunch of measurements, they're getting updated over time. And so I started paying attention to natural language processing, like what was happening, because that's another problem with like kind of sequential structure. And I was seeing things like these papers in 2012, 13, 14 that like Ilya Sutskever and like other people like that were doing with language modeling and seek-to-seek type things. And you start thinking, are these methods sort of limited to these kinds of kind of like neat, like ordinally like kind of sequence things like language, or would they also work for things like kind of like messy multivariate time series data that you have in clinical settings? And so Dave Kale, who I mentioned earlier, was the guy that they tried to recruit. I had actually met him like when I was like starting PhD at UCSD, actually at Machine Learning for Healthcare, like one of the first years of that, when it was still like, it wasn't even a conference at the time, it was like a symposium. And so we got together, this was like second year of PhD, and we kind of had this idea of, it wasn't obvious at the time. Now, like anything that looks like a sequence, people throw an LSTM at the time, but the time was really only making headway like popularly in language. Mm-hmm. And a little bit maybe like on top of like, RNN convenant type things, like on top of like video or stuff like that. Mm-hmm. And so, we were interested, can we do much better than kind of status quo at predicting things like length of stay, mortality, recognizing diagnoses based on, and so you have these time series where like the added complications are, you have a bunch of different variables. Some of them are missing. They're observed. They're not observed at like some fixed interval on the wall clock. They're observed at like different times. If you try to like resample to make a statistic of the time series that's reflective of like a fixed like wall clock time delta, then you wind up with like missing data that's not like truly missing, but it's like missing as an artifact of like the sampling frequency. Like it wasn't observed in that window. So then what do you do? How do you impute it? Do you carry it forward?
You mean like basically you have a lot of windows where nothing happened?
Yeah. Or right, exactly. Like, say like your heart rate's measured continuously by, like automatically by the equipment. However, like the coma score is recorded once per hour by the doctor when they make the rounds. And then some like serological result, like maybe it's checked once per day, or maybe some days it's never checked or something like that, So you have, well, if you choose the time interval that's somewhere in the middle, like hourly, and you have this one thing that you're measuring that's happening multiple times inside a window, this other thing that's only happening once every like 7 windows. So, I mean, an alternative way that you could represent it is you could just say every measurement is you don't have the time tick for the RNN correspond to like a fixed delta on the clock, but you can make it correspond to the observation and say something like add as a feature, what is the time lapse since the last observation? And that's a little bit like, there's like event-based representations that they use for like music generation and stuff like that. And in our case, it didn't work as well.
So I'm always curious, like, it's funny, we've talked to a whole bunch of people from different angles in the medical field, but like, can you give me like a rundown of sort of the current state of the art in ML and medical stuff? Like, what are the most impressive results that you've seen recently?
So there's like a bunch of slam dunk results, I think. I think you have to divide up like the categories of problems. I think a lot of people, like you see a lot of kind of like the public think pieces about ML and healthcare, and they just kind of slop everything together. And it's just like, the AI is making decisions, and like, you'll have an AI doctor, and is it better than regular? It's kind of just a way that like collapses like doctorness is to like a single task. Like, sure. I think the reality is you have a whole bunch of different tasks. Some of them are really clearly like recognition problems. Mm-hmm. Like it's a pattern recognition problem, and the environment around that problem is so well understood that like if you solve pattern recognition, then you know what to do with the answer. So you don't have like a real policy problem or like a decision-making problem. You just have I put in this things like, now I'm gonna get angry letters from, I don't know, some specialist that I'm like saying they're automatable or something. But I think the things that are most amenable to this are the results like the diabetic retinopathy, where they take the retinal fundus imaging and they're able to predict whether or not someone has retinopathy and do it, say, as well or better than a physician can just by looking at these images. Mm-hmm. This is one of those things where it's like, the doctor knows what to do if they're 100% sure about the diagnosis. It's like, if you could just do the diagnosis more accurately, it's good. And then you know what to do. Mm-hmm.
And you did the diagnosis here purely from an image. So it's essentially an image classification task?
Right, exactly. Things that sort of just like reduce to like, hey, it's a pattern recognition problem. That's all we're doing. That's all the doctor's doing. And, those things you can core enough. Pathology, I think, has some of these like diagnosing things based on microscopy. Like one of the best papers I saw on machine learning for healthcare in the first year that it was a publishing conference, these people said, hey, it turns out they were attuned to the climate. They were actually writing from Uganda. And it was like the paper was very straightforward, but the problem was the A+ part of this paper is how well motivated it was. They said, hey, there's like 3 of the biggest maladies in Africa were like tuberculosis, malaria, and intestinal parasites. These things are diagnosed based on basically pattern recognition by human doctors looking at microscopy, like microscope images. Africa at the time, as was argued in the paper, didn't have nearly enough technicians to be able to like give timely diagnosis to everyone. Mm-hmm. And I think at the time they said there was something like, because it's much easier to diagnose, or it's much easier to donate a microscope than a microscopist. So there was like a situation where there were more microscopes than there were technicians on the continent. Mm-hmm. And basically it's like, if you can just do pattern recognition really accurately, you could, and you could even avoid a lot of the pitfalls that normally plague machine learning. Like you could standardize the equipment, just send everyone the same damn microscope, the same mm-hmm. phone camera for taking the picture, et cetera. Mm-hmm. If you can get like, so they train a simple convnet. There was not a lot of like, you didn't need to do anything super novel methodologically. And you end up getting like 99% accuracy on like doing this 4-way classification among these images. Mm-hmm. He said, done, this is like an important problem. You can imagine shipping that tomorrow. Not really tomorrow, but you get the idea.
Does that really work? I see a lot of these kinds of results and I wonder, do they really work, or is it somehow like a more toy version of the real problem?
Right. I mean, I think that's almost always a concern when you look at machine learning results, right? Because the results that you see in a typical ML paper are almost always on a sort of randomly partitioned holdout set. Mm-hmm. So you're always worried about basically, hey, everything in the paper is sort of conditioned on the faithfulness to like that IID assumption. It's like that my training data and data I'm going to see in the future are really can be regarded as independent samples from the same underlying distribution. Mm-hmm. And that's almost never true in practice. And the question is like, is this true in a way that just completely bungles up everything you've done? Or is this, so an example of where there's a huge discrepancy is you have people saying that we have human level speech recognition. Mm-hmm. And then if you ever actually use your speech recognition, it's like really clear that it's nowhere near human level. So what it means is like on the training corpus, if you randomly partition it and you only look at like the maybe accuracy on like catching the, actually, I take it back. They're not looking at phoneme level error rates. They do, look at word error rate at this point, but you get the point. It's like, if you make this really strong assumption that like the training data is, and people confuse these because they use the same word. They say generalization in both cases, but one is the one is, or maybe what you might rather call interpolation than extrapolation of like, do I generalize from the training set to samples from the exact same underlying distribution?
Yep.
The other is like, can I tolerate the sort of perturbations in distribution that are like assured to happen in practice? And so I think this is the thing that people deal in a really clumsy and kind of ad hoc way with right now. And a lot of my more theoretical and methodological research is about like, what are actually proper, like sound principles according to which you can expect to generalize under, perform well under various shocks to the data generating distribution.
So, and I want to get to that, but I feel like I took you off on a tangent for no reason there. So just going back to like, so you were like,
you take me on a tangent, I'll oblige,
Appreciate it. But the other medical examples that you think are impressive, I think you're sort of laying out like an ontology of it.
Right. So I think a lot of these, like I think the retinal fundus imaging, like I'm not like, I think there's that long pipeline of productionalizing things in clinical trials, and I'm not actually up to the minute on where those are in that process, but that would be stuff that I'd be really confident would see it to production somewhere, if only as like an assistive tool that like, hey, if the doctor disagrees with this, get a second opinion.
Yep.
So that stuff I think is really out there. But then you see the other things people start talking about management of conditions, decision making, and they start training models to do things like predict what would happen based on past decisions or whatever. Now this stuff, gets way, way, way funkier, or, like all this kind of stuff that like has a flavor of, there's sort of maybe two things that people do. One is like sort of estimating conditional probabilities and pretending that they're estimating treatment effects, and that it's like acting as though like knowing probability of death given this and death given that actually is giving you insight, or really deep insight to what would happen if you intervened. Probability that someone dies given that they had a treatment is very different from probability that someone dies given that like I intervene and give them that treatment, when in the historical data this person always would have received a different treatment. Mm-hmm. So I think you have that kind of work where there's like a huge gap between the kinds of things people are trying to say about how you have sort of like two sides: people who really understand causality and therefore like really measured and kind of conservative about the kinds of claims they're making, and then other people kind of putting out like kind of associative models and acting and writing in a way that seems to confuse whether that they're associative or actually causal models in terms of the kinds of decisions they could plausibly guide. Or you have sometimes people doing things like off policy RL, where you look at things like sepsis management or whatever, and you try to say, well, okay, can I like fit some kind of, it's the same as like the RL problem. Like I've observed a bunch of trajectories sampled from one policy, and then I fit a model and I make an estimate of what sort of like average reward would I have gotten under this alternative policy. But being able to make that kind of statement is still subject to all kinds of assumptions that you need, in causality, like that there's no confounding, that the past treatment decisions are not actually influenced by any variables that you yourself don't observe that also influence the outcome. So like all these kinds of things, when people start talking about guiding decisions, making better treatment decisions, inferring all these kinds of things from observational data, I think there's a huge gap between the way people are talking and, getting things into practice. But maybe those are the very most important things to actually be working on. And then you have like the kind of like easily coordinable, like ML pattern recognition problems. Like just, can I look at an X-ray and say, is it pneumonia or not? Can I look at a mammogram and say, should they be recalled or not for diagnostics?
And so where does the sort of like time series analysis stuff that you were talking about in the beginning fit into that? Like, is that like at a point where it's, like a tool a doctor could use?
For example, the first big paper that we did on this is the one we published at ICLR, which is learning to diagnose with LSTM RNN. So we're feeding in the time series and predicting which diagnoses apply to this patient. So I think you could paint a story that's like not totally crazy about how this could potentially be useful. And one example would be, hey, I have a new patient. I have them, there's some kind of emergency. I have the patient, I have them hooked up, I'm recording data. I want to be able, if I'm not sure what the diagnosis is, it would be nice to be able to have like a short list. So that's part of how we evaluate it. It's like, I could look at what the machine thinks are the 10 most likely diagnoses. And I could say, okay, I'm going to make sure that I check, that I include these things in the differential or something. It would be like some kind of sanity check. Like you're using the machine as like a wide pass to just make sure that you're considering the right diagnosis. Now, is that actually useful directly? Like, in its form, you know what I mean? Like there's a question of, could that in general, that kind of idea work? And is this sort of maybe a proof of concept that it's plausible? I think we can maybe make that kind of argument. But in terms of like for these specific cohort, like for the patients in the ICU, is this really something where what we did is directly useful? I think, I think there's no way you can have like kind of this proper, like make, just, I don't think there's, I think you have to really like lack humility to kind of go out there and just kind of say like, in an unqualified way, like this is actually useful in practice. I think probably not. Like, I think for a lot of those patients, basically, we're able to demonstrate this technology is capable of recognizing these facts about these patients. But in reality, the diagnoses for a lot of these patients was already known. We're just showing that we can figure out what it was from certain trajectories, certain traces, certain measurements. Mm-hmm. But if the doctor already knows the diagnosis, what do we really do to improve care? And I think, this is sort of how, my research has maybe evolved. Is I started off maybe asking a lot more of these. The interesting thing was representation learning, and like, can we just do anything useful with these types of weird looking data? Like the standard thing you remember from like the early 2000s or whatever is like always like find a way to represent whatever you're working with is like a fixed length vector, and then feed it into like, menu of scikit-learn models or whatever, and see what comes out. It was exciting to say, could we do with things like, could we actually get signal out of these varying length time series with these, weird missingness patterns and whatever. But, at some point, okay, like the representation learning thing has like happened, and we know that we can do this. And there's less things that are like truly exciting there, because we sort of know we have a good set of tools between sequence models and convnets and graph convolutions, et cetera, for representing kind of various sorts of exotic objects. And that's no longer maybe to me the most exciting thing. So the most exciting thing is, okay, we can do function fitting. Let's say we can do function fitting. Let's say we even believe that we've solved function fitting. Like, what's next? Like, that doesn't get us to like the AI doctor. That gets us to like, maybe we've solved like retinal fundus imaging. But like for the most part, and here's another problem to just like poop on my own work a little bit more. And like what we all do is one thing that we often do is we make these statements about, what is human level performance on some task, but we often don't think like about the wider scope. Like we were sort of myopically focused on in ML, you're really told like, I've got my inputs, I've got my outputs, I've got my loss function. And then like the room inside there, that's where you dance. Right. But think about the diagnosis problem. This is like an example I like to give my students is, the way we cast the diagnosis problem in ML is like, given all this measured data, can you infer, more accurately or as accurately as a human, what is the applicable diagnosis? But was that ever the hard part? Like, like the extreme example is like, if the doctor gives you the test for like Lyme disease and the result is positive, the fact that the machine can more reliably look at the data that contains that fact and say you have, that's an extreme example, but you get the point. It's like, given that you were already like kind of routed to the right kind of care and had the right measurements done and whatever, maybe the machine is good at doing inference about what you have, but maybe that was never the interesting part. That was never the hard part. That was never the part that really demanded that you need a human in the loop. The hard part was seeing a patient, you have no data about them, and you have to make these hard decision problems. Like, decisions are not just about treatments. There's also decisions about information revelation. So that's something we focus on a lot in the lab now, is these like weird problems where the decision is what to observe. Mm-hmm. Like I want to figure out what is the best drug to treat some patient. I got a bunch of people coming in. I can run some tests, but I can't run every test for every patient. I could try some treatments. I can't run every treatment for every patient. So like if I were to cast this kind of problem, you can make it really abstract. You could just say like, I've got some kind of set of variables. They're related by some causal graph. In every time step, you get to observe some subset of them, and you have some budget that, constrains like which ones you can, intervene on. But the point being that it's like the set of data you observe not being taken like, just like by God, given to you as something that you take for granted, but rather, sort of widening the scope of what we consider to be like, sort of like our jurisdiction as like people thinking about decision making and automation.
Well, I mean, I'm obviously a big fan of that area of research, because I do think in practical applications, you do actually have some control over those things, like what data you want to collect and how you want to collect it. And I do think it's a messier research problem, but probably more directly useful in a lot of cases, just because the sort of function fitting stuff is so well studied, relative to the impact that it can have.
Yeah, it's also more like sometimes, like I think there's a way that people have like you've seen this before. You were like Stanford math or something. Like you've seen like the kind of weird like hierarchies that people form of like certain within a discipline, this idea of like, okay, there's like the mathematicians are on top of the physicists, are on top of the chemists, are on top of the biologists, are on top of the applied whatever. And like this thing happens in ML a little bit with like theory and application, where people kind of get snooty. And I think one thing that's weird is that there's like two axes that get collapsed there, of like theory and application, and like theory and or like mathematics and empiricism, like different mode of inquiry versus like method versus real world. And I actually think that like that's like maybe it's true that like theory is somehow more philosophically interesting than just like benchmark applications, like than just empirical pursuit on methods. But the application is like a different axis. I actually think that like the applications are super philosophically interesting. Like I think they force you to ask, because they ask you to ask questions that aren't just like mechanical. You have to ask like the normative questions, right? Like the thing that I think is exciting about applications is that nobody told you in the first place what is worth predicting. Like that by itself, like convincing someone that like this is actually a problem worth solving.
Well, it's funny, I was just reading, one of your papers that you pointed me to on essentially collecting more data. The way I would describe it is like, it's about kind of collecting more data to get the model to learn the things that you want or the connections you want, versus the sort of like spurious connections. Like you had a good example of, like models predicting like seagulls because they see the beach. And, we sort of assume, you make this point that's evocative of like, we assume that that's bad, but it's kind of hard to articulate exactly what's bad about that. Like, I guess it hurts you in generalization maybe, but if it doesn't hurt you in your data set, it's probably hard to distill what's bad about that.
Right. You have all these papers out there that are saying like, like sort of using, saying the model's biased or the model depends on superficial patterns or spurious patterns, or without any kind of clear sense of like what technically do they mean. And what we get at that is trying to say, here's something that I think causality has to offer. Like I think a lot of people talk about causal inference, like really focused on the wrong thing, like thinking like, is it useful or is it not useful? Like, can I take, like the Perl machinery and go apply it on the real data and estimate it and get the number? And economists are like, I think more like focused on that. Like, can I get the number? Can I estimate it? But I think like one thing that's nice about sort of like Perl's perspective, and I think that is really important, is that it's like causality is not just useful because of you can actually estimate the causal effect. It's important because like you can coherently express the kinds of questions that you actually care about. And even if, at least within that, like you can have the way of making coherent statements about things. Like, so in this case, like it gives us the vocabulary of to say like, in what sense is it wrong to depend upon the beach when I'm saying this is a seagull? Is that like, it's not what causes it to be a seagull, right? Or I think like an example that I like a lot of times is like, why is it not right to base lending decisions for who you give a loan to on what shoes they're wearing? And so part of it could be that like, that something about how shoes relate to finances, like something about the structure of the universe, and you're able to think in your head, what happens if I intervene on your shoes? If I take someone and I intervene on their shoes, because people can intervene on their shoes, right? They can, if everyone who wears Oxfords to the bank gets a loan and everyone who wears sneakers doesn't, people will intervene. And to say, is this a reasonable procedure? One reason why you say, this is why I want it to depend on this or not on that, is to say, what would be, I can do this counterfactual kind of simulation, say, what would happen were I to intervene on that? would this change your ability to pay? Would this change the applicability of the label in the image? Right. So I think like for us, like the big insight is just to think of it kind of coherently as like, think of like semantics as actually like, sort of being a causal in a way. Like this is what causes the label to apply.
Yeah.
And then it becomes maybe well defined, right? Because I mean, the benefit that we have is that in our paper is the learning the difference that makes the difference paper, we actually have humans in the loop. So we're saying, hey, this is something that may or may not be actually identifiable from the observational data alone, but it's something that we can get via the annotators. Like they're revealing to us, like we have this example about genre in movies, right? So if you train a classifier on to predict like sentiment on IMDb movie reviews, you find that like top positive words, you do something like you just train a linear model and look at like the high magnitude positive coefficients versus negative. The high positive ones would be like fantastic, excellent, whatever. Negative ones would be like terrible, awful. But the positive ones also have like romance, and the negative one also has horror. And you're like, that's wrong. And like, why is it wrong? It's like, because then like Jordan Peele comes out of nowhere and starts making all these great horror movies. And your model's inferring that they're bad because it's like kind of, dependent upon this thing that this signal that's not durable over time.
I was kind of thinking in that example though that I think romance movies are generally better than horror movies, and maybe the average human agrees with me. So there is some sort of
right, but that's an associative statement, right? You're saying they are generally better, and that actually does seem to be what the general public agrees with, right? The problem isn't are they generally better? It's does it have to be that way, right? Is this like, could you imagine a world in which tastes shift and the talented movie makers really shun romance movies and they become bad? I mean, so there's a sort of embedded assumption here. It's something that we're looking into a lot now. And for anyone in the audience who's really interested, there's a lot of great work by a scholar named Jonas Peters, who's maybe more of a theoretician, but approaches these problems. And, there's questions about, you say, partly the question, like one way of motivating this is you think about robustness out of domain. You say like, when I go out into the rest of the world, is it always going to be true that romance is good and horror is bad? If I go to a different culture, do I expect that like that can, if I can move to a different state, do I expect that like this is the durable part? And so, one kind of like assumption here is that the things that cause the label to apply, that these things are, that this relationship is actually stable. So you can imagine that like the things that actually signal positivity versus negativity in a document, that this is relatively stable over years, but there's a complicated relationship in the background that influences, is the perceived sentiment positive? Is the movie quality high? What is the budget of the movie?
Right.
What is in vogue? Like, what are the houses spending, money on? What are the publishers spending money? What's getting distributed? Whatever. That these things are all changing, but that the causal features are that those, like, you could think of like, if there's a structural equation that like says like, what is a perceived sentiment, from the text, that like that thing is actually relatively stable over time compared to these other features. And so, and that's part of our empirical validation. And so we have this model, right? We show that what we essentially get people to do is to rewrite the document. They're told to make a sort of a minimal edit, but it should alter the document such that it accords with the counterfactual label. So this is originally a positive review. We say edit the review without making any gratuitous edits such that it is now a negative review. And when they do that, you wind up with a new data set where for every original review that, had horror in it and was positive, now there's a sort of bizarro counterpart, and it still has horror in it. And the reason why it has horror in it is because of the instructions. The instructions said, don't make gratuitous edits, like don't change facts that like are not material to the sentiment. And so this is something that like we can argue about whether it's actually statistically possible to have disentangled that horror is versus isn't a causal feature without that intervention. But once we have this document, we say all the horror movies still contain horror, but their label's been flipped. All the romance movies still contain romance, but their label's been flipped. Because other parts of the document, the ones that like, actually needed to change in order to flip the applicability of the label, have been changed. So if you train the model on the counterfactually revised data, you find that like the coefficients flip. So like excellent and fantastic are still positive words, but now horror is also a super positive word. And like terrible and awful are still negative word, but romance becomes a really negative word. And the cool finding is if you combine these two data sets together and train on them, they kind of like wash each other out. And so you find that like all of the things that look like they don't belong on these like lists of important features actually seem to kind of fall off. So we're dealing with causality here in maybe a more gestural way. We're not using like the mechanics of we're not using like the mathematical machinery of like graph identifiability or anything like that. But we are getting this interesting kind of really suggestive result on real data. And when we look at it, just to that last point that we were talking about with generalizing out of domain and are the causal connections durable, one thing that we looked at in the camera ready version of that paper is we say, okay, we trained it on IMDb. Let's now evaluate it on Yelp, Amazon, et cetera, et cetera. And when you go to those other models, the model that was trained on the counterfactually augmented data, which is like the combination of the original and the revised, does much better out of domain. Now, this is not guaranteed to happen. Like this is like the supports are not shared. There's a lot of funky things happening statistically here. But what I think is suggestive here is it's like, it does sort of agree with the intuition that you say on movie reviews, horror versus romance is like an important part of the pattern. Like that's a real clue. But once you start looking at like Amazon electronics or something, that's no longer actually maybe a durable pattern. Someone's like, oh, my, Discman was such a horror or something.
Well, I think like what I really liked about that that paper was sometimes I feel like
at least for me, some of the like highly theoretical papers
kind of point out problems and they're kind of hard for me to even engage with because I don't like sort of see the practical effect. But you have actually such a like a simple mechanism proposed here that actually worked in your case, which I thought was super cool. And I've noticed like in my 15 years of working with ML teams, a lot of teams naively intuit to do things like what you're saying, and they usually feel bad about it. Like they feel like they're kind of doing this like weird manipulation of the data to try to get it to generalize better by literally like, often like rewriting the text in structured ways. And so, I don't know, I just really enjoyed it's a cool paper with a cool, theoretical motivation that I think is really important, right? Of kind of like eliminating different types of bias and making things generalize better, but then also an interesting, like, practical way of doing it. That kind of feels like, it's reminiscent of like active learning techniques and things, but more interesting.
Cool. Yeah. Thanks. It was fun to write. It was scary for a minute though, like because we're like asking these like workers to do this weird kind of thing and like not sure if the results, and it was sort of like a little bit of coin for, relative to
sure,
like, the pot of discretionary funds at the time. So it was sort of like, there was like this moment of like, well, what the hell are we doing? But yeah, it was nice that it worked out. I mean, I think that's like just mainly one of the differences between like a sort of like, not to like get into like academia versus industry culture wars, but I think like something that like academia done right affords you is like, it's not like we need to get the product out or something. It's here's this, like, we have this thing we're after, and it's like, you have that intuition of like that this mechanism might be interesting, but the next step isn't like just like do it or not do it. It's like that like the ability to have a PhD student spend a lot of time to have like kind of arguments about this for a couple months of how do we want to do this, agonize over the experiments, kind of go back to like, let's say we drew a toy causal model in our heads, like what does this correspond to? And so we have a lot of follow-up work coming from that now. But the fact that you get that, like, for somebody, it's like their full-time job for a year is like thinking really hard about a problem. You can get from like, this is something kind of wacky, maybe let's try it, and then call, versus like, okay, now this is your full-time job for a year. Is we're gonna think really hard about this one problem.
Yeah, it's super cool. I was kind of curious. I was also looking at your like another recent paper that you pointed me to that was like a little bit kind of harder, for me to parse algorithmic fairness from a non-ideal perspective. Could you describe what you're doing there?
Yeah. So this is a paper with, so I actually have a postdoc in the philosophy department now. So he's working with me and David Danks. And this paper is really about, I guess in some sense, it sort of touches on the high level theme of like identifiability, which is, you know, there's a lot of like well-founded concerns. Like if you're going to have decisions automated, these are decisions that in general are addressing problems that like are sort of like ethically consequential, whether it's like bail decisions, lending decisions, hiring decisions, mediating the flow of information, any of these decisions, all the normal questions that you have about and concerns that you have about fairness and equity and justice, continue to apply. And I think as machine learning has gotten widely deployed, people have sort of become more and more aware of this. I think in 2015 I was like starting a blog, or 2016 on this. It was sort of like, didn't even know there was this community out there of like people working on it. There wasn't conferences like the fairness, accountability, transparency, and whatever. And now it's kind of blown up, and it's blown up for a few reasons, but I think there have been a few like pivotal things that caught people's attention. Like one, there was like the hiring screening thing that was filtering out resumes by female candidates. Probably the biggest thing that caught people's attention was the ProPublica article about machine bias. This is talking about recidivism prediction models. This is predicting who will get rearrested if released on bail. And so, you have these systems, and suddenly there's basically the claim is these systems are being used to guide sentencing decisions or maybe like bail release decisions, and they're biased against Black people. And like this is obviously a big problem. And then immediately sort of people, there sort of arose this crisis of like, well, how do you quantify that? What is the quantity that says there's bias? So someone says, well, let's compare the false positive rates, compare the false negative rates. This whole kind of literature, let's compare just the fraction of people that are released on bail among all defendants. And you say, well, the distribution of crimes among defendants are maybe not the same. You have these metrics that are based on thresholds, but you're not necessarily considering like all aspects of the distribution. So people come back and like these kinds of criticisms. And there's sort of like emerged this whole community that spends, of sort of like algorithmic fairness, which is looking at, these kinds of problems and trying to say, what are formal ways we could define fairness? And so, you might say the model should functionally behave equivalently regardless of what your demographic is, fixing all your other data. And then the criticism against that is you say, well, that's meaningless, because if you withhold gender, but you have access to say all of my social media data, or have access to some sufficiently rich set of covariates, someone's gender is captured there. So what does it mean to say that you didn't explicitly show that bit in the representation? If the information's there, you have it. So what does it mean to say it didn't impact your decision? Mm-hmm. And so there's this whole kind of line of work that's sort of trying to express this problem formally. And they're trying to express it in a world where everything is sort of defined statistically, in a world where basically what we know is there's a set of covariates, which are just like some numbers, some distribution. There's, we'll call that X. There's a demographic indicator. It's like, are you in group A or in group B? There's the predictions by the model, and there's the ground truth. And, it's just sort of like now trying to say, what are the kinds of parities that we want to hold? So maybe say I want an equal fraction of the population classified as positive, whether they're in group 1 or in group 0. Mm-hmm. I want the model that doesn't actually look at the demographic. I want them to have the same false positive rates. I want them to have the same false negative rates. I want to have the same both. I want to have, so there's people propose it.
Sorry, I'm trying to like connect these to like, as you say, like false positive, false negative. I'm just imagining the cases. I mean, can you say these in more like
sure
real cases so people don't have to make that?
Right. And actually, like, this is sort of the kind of focus of a lot of our critique, is that, you could just describe the world in those terms and zoom out and start talking about various kind of equations. And you could say a whole lot of things that seem intuitively plausible or reasonable. Like, I want this to be equal to that, or I want but it's like, what's missing from this whole thing, so when people talk word to vec, they say that the word to vec is biased, word to vec is discriminatory, word to vec is racist. What does that mean? What actually is even the category of object to which these statements apply? And you kind of realize really quickly that we've sort of abstracted so far away from the problems in that description that like we don't have the relevant facts to say what is fair. So, example would be, if a model is being used to predict whether or not you're going to commit a crime, and being falsely predicted as going to commit a crime means that you get denied bail or something, being predicted positive is really bad. If the model's trying to predict who's likely to, conditioned on were they to be hired, would be likely to get promoted, and it's using this to guide like resume screening or something like that, then like getting predicted positive is good. And so in one case, maybe you'd be concerned about false negative rates. Like, is someone who really has the skill level being denied the opportunity for the job? In other case, you'd be concerned about false positive as someone who wouldn't commit a crime be flagged. But sort of lost in all that conversation also is whether or not something is like justice promoting or like justice, whatever your sort of like normative positions are. I mean, you fix any set of like normative concerns that like, you say are define your morality. I would argue that, even anywhere within kind of the normal spectrum there's still a problem that like these descriptions of the problems aren't sufficiently rich to sort of say what you should do, because the facts that are omitted are what actually is the problem I'm addressing. If there's disparities in the distributions initially, like what caused that to be? If I'm making a decision, what actually is the impact of the decision? What is the impact, how does it actually help or hurt people if I change this decision-making process? So an example might be, let's say you have a process that is determining like admissions to higher education. Like in this case, intervening in a way that created more parity in the decisions, I'd argue, or created more kind of demographic diversity in the ultimate decisions, I'd say is like a good thing. Now that's my sort of like normative position. Maybe someone who's like not as progressive disagrees, but we can disagree about that. Even fixing my set of positions, if you change the situation, you say the issue is something like you're certifying surgeons or something, does subjecting someone to, say, a different standard across demographics actually help or hurt their careers? Like, in this case, that might be a bad thing, because if you were to alter a decision-making process that was, say, like a safety certification, then you sort of maybe the reality, like the real world impact would be to sort of like almost like legitimize like discrimination further down the pipeline, right? Like where now patients are going to treat doctors differently because they know they were subjected to different tests. So there's these different decisions that have different kind of, but because of like what actually is the decision you're making and what actually is the impact of this decision, something that sort of looks from a technical perspective like an identical problem could actually have a very different interpretation in terms of what is the sort of, justice promoting policy to adopt. And so the concern is that by abstracting away from all those relevant details, you kind of lose sight of this. And what we ended up kind of finding, and this is really Sina gets credit for this, and I think the big contribution in this paper is really just making this nice connection across like a very wide interdisciplinary boundary, is that this is sort of almost exactly in some ways a recapitulation of a lot of arguments that have been had, for decades in the moral and political philosophy literature. And there you have sort of two approaches to sort of like theorizing. You have many approaches, but just like one of the axes of like differentiation and like how to theorize about these questions of justice is like the ideal versus the non-ideal approach. The ideal approach says, let's just imagine a perfect world and just say that things that hold in the perfect world, we should just fixate on some one of them and try to make our world look more like that. It's sort of saying, so you could think of the sort of like reason why this can go wrong is you can imagine, like, for example, this kind of theorizing has been used to sort of oppose policies like affirmative action in a sort of blanket way where you just say, well, in the ideal world, we'd all be colorblind, so therefore we don't need affirmative action. Like that's unjust. The non-ideal approach is in some ways like a more pragmatic way of looking at these sorts of problems, where you sort of say, right. So among other things missing from the ideal approach is you don't say anything about what you say. How should someone behave in a world that is like already in some kind of like ideally just or fair state, and where everyone else is completely compliant with what like justice demands of them, and just like your job is to like not fuck it up. That's very different from the non-ideal approach, where you're sort of saying, hey, I live in this world. There are existing disparities. Now, given that I live in this world, given that there are these disparities, given that there's all these people who are bad actors out there, what is the justice promoting act? And to recognize that that's not necessarily the same thing. And then you have to be concerned with, well, like, what are the disparities? who has the right or the power or the like legitimate mandate to like intervene on what kinds of decisions to try to like rectify them, and then what are the policies that are actually effective. And so I guess these questions become, if you remove those details, these questions become kind of vacuous. I'll give you an example. Would be higher education admissions. So if you just say like, okay, what we want to have is same fraction admitted among men and women. And you just say that, like, I think most of the people saying that aren't actually paying attention to the fact this is among what population, right? So if you were to look at like a typical like school, there's already a huge gender disparity in the application. So if you just accept people at the same rate, so there's all these, like, if you fix any one problem and you really start going deep, you see that there's all these other details that what is the right thing to do, what actually counts as like, the fair decision-making process hinges really like, precariously on a bunch of facts that are not represented in like the problem descriptions. And so I think, that's sort of our angle in this kind of critique, is to sort of like cast a light on that, like, there's this sort of common saying in the fair ML world, like, oh, we have, 72 definitions of fairness or something like this, like, look how many definitions, and the kind of, maybe TLDR is sort of like, we don't have 72 definitions, formal definitions of fairness, we have 0. And the reason why is because, like, you have 72 different sort of like fairness inspired, like parity assertions. But the real actual question of fairness is sort of the question of what are the material facts that you need to make a determination about, which apply in a given situation.
Mm-hmm. When you look at the different topics in machine learning, is there one that you feel like people spend way little to time on, like one that like you just think like has way more impact proportionate to the amount of attention that people give it?
Like, my only reluctance is that there are things that are sort of, at least like the trajectories in the right direction, like people are paying more attention. But
sure.
I think in general, like, coming up with coherent ways of addressing, problems like that are sort of beyond the IID setting is really key. And I would subsume under this, like, both addressing causality and mechanism, and also include like robustness under distribution shift. Like, you have like one very narrow subset of distribution shift problems, which is like the minimax kind of like adversary setting, where the adversary is able to basically, you have the same underlying distribution, but it's like the samples are composed with some asshole who's able to like, manipulate your data within a L infinity ball. So you've got like 4 million people working on that problem. But in the like broader set of like, what are the kinds of structural assumptions that allow us to generalize under distribution shift area, I think we have maybe, like this is the problem that plagues every single real world ML setting. And that, even among papers that like sort of say they're working on this problem, I think the vast majority of people don't seem to even understand like the basic concepts. I think it's like, for this technology to actually be usable, I think we need to have like coherent principles under which we can make confident assessments about when it's going to be reliable and when it's not. And so I think, that's obviously a little bit biased maybe towards my research agenda, but I think
that's fine. That's why we asked the question.
It really is. That is sort of, I guess that's sort of like the common sense wisdom for how you should choose a problem, is like, you should pick something that you think is important and like underappreciated, not overappreciated.
Yeah, fair enough. I think actually you should feel happy that you're in that situation. I think somehow it's not logical that people get stuck working on problems they don't think are the most important problem, maybe, or at least based on some of the conversations we've had.
All right, part of that is people being lazy. Part of that is like the friction, right? It's like if you had a thing that you thought was important once, and then you like built your lab around it, you got funding on it, and your whole life revolves around maintaining like this research thrust. So I guess now that I'm running a big lab and now that I have finances to worry about and all that, I'm a little bit more appreciative of the handful of people out there who really sort of did make these like hard left turns at some point. Like, I think Michael Jordan's a nice example of that. Like, someone is like kind of, I think Jan LeCun said he's like Miles Davis or something, but like, it's like, okay, each decade he had, it's like neural networks, Bayesian non-parametrics. Now I guess it's like mechanisms and markets or whatever he's working on.
Well, you've made quite a leap from music to deep learning, I think.
Yeah, I think it's time for me to retire. I think 5, 6 years is like the That's the left turn. That's the left turn limit.
So the final question, which I don't know.
I have a mortgage now though, so it's a little bit harder.
But you have a fancy computer behind you there. I don't know what.
That's actually my Power Mac from like 95, 90, 97 maybe.
Does it work?
Oh yeah, like I've still got. Did you have one?
Something like that. Yeah, with like HyperCard and yeah.
Like I think there's still like Oregon Trail and like Diamond, like all those like weird freeware games like Max Ski.
Oh yeah, Max Ski.
Epic.
So final question. When you look at sort of taking machine models from the sort of like ideation or the sort of like research paper to actually deployed in production, where do you see the biggest bottleneck or things falling apart the most?
I think the biggest bottleneck is still problem formulation. Like I think if we were to be really sober of like most of the things that like people thought they were going to do, and then you look at like the way they propose to model the problem and then like the data they could actually collect and then like what they could produce and like does this in any way actually address the problem that they thought they were going to. I think those look like, I think those would be, I don't know how you would collect that statistic and like, there's some like measurement questions, but I think it would be like really depressing. It would be really sobering that I think most things people think they're going to do are either like kind of goofy and who knows if they work, or just like not relevant, will never get used. And I think that's like figuring out like where there's really a well-motivated application of machine learning and what it is. There's like that weird nexus of like the kind of pieces of information that you're asking people to put together. I think this is why, like, not to be like data scientists are great or whatever, but like why I think like people who are really good at this job are like really hard to find in some way. And at the same time, it's kind of puzzling, right? Because I don't think that the great data scientists are in general great or even like rateable mathematicians, right? I think for the most part, there's of people like actually touching data are mostly lousy mathematicians. And they're usually not world-class engineers. So I certainly am not. And like, what is it? And it's like, I think it's this weird combination of like the weakest link kills you. And like, you have to sort of see, to be, I think, good at doing this applied work, like what is the important problem? You have to also know like, what is the current technology like in the ballpark of being able to get you on this kind of problem? How does it match against the data that's available? And then I think you have to, at least at an intuitive level, do kind of this non-statistical thinking that's sort of like what's actually the process where you're deploying it. So like the X-rays or whatever it was we were talking about, like the retinopathy imaging or something. Like this is sort of a good application of machine learning because what those images look like isn't changing over time. But you look at all these places in industry, people trying to like build recommender systems and do all these things where it's basically, it's like totally incoherent. Nobody has any idea what happens when you actually deploy it because you're modeling something that's only like in the vaguest or weakest of ways actually related to like, what you think would like to be predicting. Like you're predicting clicks or whatever. You're predicting a condition on the previous set of exposures, almost never with like any kind of coherent accounting for what happens when you deploy the model. I think like this obstacle is like people making that, like, I think this is always in some ways the hardest part of intellectual work in this area is the bindings. It's not the, like the first level difficult is like technical skills. Like, are you a good programmer? Are you a good engineer? Do you write proofs that are correct? Do you do whatever? But I think like the like conceptual difficulty in working in machine learning is like, do you make the connection between like this abstraction that you possess and the world that like you're actually trying to somehow interact with? And that to me, I think often is where all kinds of things go off the rails. I think where a lot of even like good academic work goes off the rails is like, you can go down some rabbit holes asking like really like second, third order, like theoretical questions about these fairness things without ever asking of like, does this actually map onto any real world decision that I would want to make? Does it actually help someone with a problem that I like purport to be motivated by? So, I would just say that, I mean, I don't know if that's like kind of a banal answer, is like,
no, it's great.
Asking questions the right way or something, but.
Sure. Well, thank you so much, Zach. That's, thanks for taking the extra time. That was super fun.
Yeah, for sure. Thanks for having me.